All right, we are going to start Chapter 7 today. Your Chapter 6 homeworks will expire within the next couple days. I think one's due tomorrow. Make sure you finish those up. If you have any questions, please voice those questions and talk about them. But starting Chapter 7 today, giving you a little bit of an introduction to what we're doing and maybe why we're doing it. It might not be, after a couple of days of doing it, you really see the purpose of what we're doing. And some people, go through the whole chapter and don't see the purpose. Okay, but we're going to start dealing with what we call it's called analytical trigonometry, and it just basically means we're going to be doing a lot of stuff by hand, using a lot of algebra to rewrite expressions. Okay. If you're a person who likes like puzzles, okay, and brain teasers and stuff like that, not to say that if you really want your brain teased inside of math class, this is going to do that. And those of you that can see puzzles and manipulate things are going to probably do well with this. Those of you that are creative are probably going to do well with this. In the past, I've had people breeze through this and have no trouble and understand exactly what we're doing. But I've also had people that, really struggle with it. And one thing I want to kind of remind you of is if you do struggle with it, it's not just something you can give up on, because it's going to come back and haunt you at some point if you give up on it, okay? Because of how much this stuff is used at the next level, okay, and in the next course. And even further on in this course, we're going to do a lot of this stuff to kind of learn and to prove other facts in trigonometry. Okay. A byproduct of all of this is that you're going to get really good, hopefully, at some of your algebra skills. Dealing with fractions, adding fractions, subtracting them, multiplying, dividing them. You get really good at that. You get good at recognizing why we want to use an LCD when adding fractions and subtracting them. We can use any common denominator that we want to, but an LCD is beneficial, and we'll talk about why as we do some of these questions. You'll learn things about, why, it might be appropriate at some point to multiply by conjugates and recognize, what do we do with, when we divide a fraction by a fraction, that kind of thing, okay? So there's a lot of algebra that's going to happen that we have to first have somewhat of a rough understanding of what that algebra, what those rules are, but then we start getting to refine those skills as we do more and more of these examples. First thing, as we go through this, I guess I've said identity a couple times maybe already. We got to talk about what an identity is, which we did talk about. I think it was in chapter 5 when we first introduced sine squared x plus cosine squared x equals 1. But an identity is an equation that is always true, no matter what you choose for your x value, or your whatever your input is. It doesn't have to be an x. But no matter what you choose, the left-hand side is going to be identical to the right-hand side every single time. And if you think logically about it, it's kind of interesting, I think, that happens, because if we follow our order of operations over here on the left, okay, let's just choose x to be, an easy one would be 10. If x is 10, don't we put 10 in here and do that subtraction first? So we get 7. And then the order of operations says, okay, now take your 2 times your 7, and you get 14, right? Order of operations tells you to do what over here if x is 10? Yeah, now you do your multiplication first, you get 20. Then you do your subtraction. Does it still give you 14? Yeah, okay. And 14 is equal to 14. That's a true statement. And what we find out is, regardless of what we choose for x there, as long as it's the same as the x that we put in there, we'll always get something analogous to this. We'll always get a true statement. Is that all right with everybody? And that's referred to as a linear identity, because it's a linear equation, right? Okay, x to the first power in both those. Over here, this is a rule that you guys have seen and dealt with, and a lot of your algebraic rules are identities. For instance, like a plus b squared. We know that becomes a squared plus ab, 2ab, plus b squared, right? Okay. That comes from an identity, okay, or an idea about identity. Same thing if I make it cubed or something like that, okay? All those like binomial expansions that we've talked about in the past. So if I have x plus 1, no matter what I choose for x, let's choose, I don't know, 10 again. Doesn't order of operations say make this 11 and then square to get 121? Okay. Then over here, we square the 10 first, multiply 10 by 2, and we get that. Now order of operations says add all that stuff up, and we get 121 again, right? So that is a true statement. That's a quadratic identity. Okay. Now we get to what we're going to predominantly deal with in this course. Is we get our first one of our first real useful trigonometric identities. All right, we actually talked about this before. We talked about, I think, secant, cosecant, cotangent. Okay? This is sine squared x plus cosine squared x equals 1. That's what relates sine and cosine to one another. Okay, and we've seen that so many times using the unit circle. If the x value is your cosine and your y value is your sine, if you square both those coordinates in the ordered pair and add them together, you will always equate that sum to 1. And that's always evaluate to 1. So that's an identity. No matter what x value you choose off, right? It doesn't have to be off the unit circle. Just any x value that you choose as an input. Okay. Does that make sense? So that's a trigonometric identity, and that's, like I said, that's what we're going to deal with for the most part. Here are the trigonometric identities that we have already discussed in some aspect throughout the course. Obviously, you got your reciprocal identities, and that's kind of the way we're going to write them. It does maybe shed light on the possibility of us also having things like, if I can write cosecant as 1 over sine, then I should also be able to write sine as 1 over cosecant. Does that kind of make sense? Okay. Those relationships that there should be 2 more like that for secant, secant of x and cotangent of x in regards to cosine and tangent. And I'm not going to write those, but there are those identities as well when we talk about the reciprocal identities. And that's the thing, when we see the identities that are up there, that they're kind of in the most traditional, most fundamental format. Okay, we can alter things, we can change things a little bit, and to develop additional identities. Okay, for instance, based off our algebra skills, if I just look at that cosecant x equals 1 over sine x, I could multiply both sides by sine x, couldn't I? And get cosecant x sine x is equal to 1. Does that make sense? And that's an identity. And hopefully it makes sense, because aren't cosecant and sine reciprocals? And the definition of reciprocals is, we call them multiplicative inverses, right? They give us our identity of 1 in the real number. So when we multiply reciprocals, our product is always 1, and that should make sense to us. But I guess what I'm trying to say is, when I give you an identity, there are various forms of that maybe. Okay. So for instance, looking at that Pythagorean identity, and we've done this practice a little bit. If I look at, and these actually tend to be ones that you use a lot. We got sine squared x plus cosine squared x equals 1. Could I do this? Should I take that sine squared x and move it to the other side through subtraction? And now I've got another identity, cosine squared x. That is always going to be the same as 1 minus sine squared x. So as we see an identity, and especially if there's addition, subtraction in it, there are various things you can do to transform it to create other identities. Okay. Now those other identities, we're not going to try to memorize. We're going to know. We're going to try to learn that they exist. Maybe have somewhat of a vague memory of them. I'm not saying learn them by heart, but there will be a necessity at some point to be able to alter the Pythagorean identities that are up there to get, maybe 1 minus sine squared x, or 1 minus cosine squared x, to see what that is equal to. That kind of makes sense? If we're to learn all the identities, there's an infinite number of them. We'll kind of talk about that here as we move on through some examples. We try to kind of learn the fundamental ones, the ones that show up the most, the ones that are most useful to us, most practical to remember, and then the other ones, you know, they'll come and you might see them once or twice in the whole semester. Okay? So it doesn't really make sense to use it. Does that make sense, everybody? So we're going to see here in a little bit that expression where it says cosine t plus tangent t sine t down here in example 1, we're going to find out that that is exactly the same thing as secant t. Okay? But we'll probably never, throughout the rest of the entire year, ever see that setup of ratios with those operations between them again. So does it make sense to store that in my memory as secant t? Probably not. Okay? What makes more sense is to be able to understand how a tangent transforms to something different, and then we know our algebraic properties and our rules of algebra, that we can actually transform that to secant t. A lot easier than memorizing that it is secant t. Okay? So that's kind of one of the, I guess, purposes of this task is to realize that your algebra skills and everything that you've already, all the work and dedication and effort you put into learning PEMDAS and the learning, you know, work with fractions, work with radicals, all that kind of stuff, is a much more useful set of skills than memorization is. Okay? Because they're going to get you everything that you need. It might, you know, take 10, 15 seconds, maybe 2-3 minutes at the most sometimes to transform something, but that is much better than your memorization, because those skills won't leave you, memorization will. Okay? Does that kind of make sense, everybody? So these Pythagorean identities, we talked about them a little bit. That middle one where tangent squared x plus 1, that is developed simply by looking at this one and dividing everything in here by sine squared. Or sorry, by cosine squared. Okay? If I divide that by cosine squared, divide that by cosine squared, divide that by cosine squared, what's sine divided by cosine? Tangent, right? And it's squared, so it's sine divided by cosine times sine divided by cosine, so it's tangent divided times tangent. Does that make sense? So sine squared divided by cosine squared gives me tangent squared. What's cosine squared divided by cosine squared? 1. And then what's 1 divided by cosine squared? Secant. Does that kind of make sense? So this one here is a byproduct of this fundamental one. Okay? But it's used enough that we memorize it. Okay? Or that we try to memorize it. But if you forget it, me, for instance, I've taught this thing for probably like 12 years now. And if you would have asked me at the beginning of the trig course what that one is, I don't know. Okay? I get it confused with this because these are very similar. I get them confused all the time. But I know that they're both developed by either dividing everything by sine over here, sine squared, or dividing everything by cosine squared. And I can quickly generate these. Does that make sense? And that's the thing with all of these, is that you should be able to quickly generate them through relationships that we understand about the unit circle. For instance, these even odd ones. Okay? Sine of negative x equals the opposite sine of x. If I ever get a negative argument, okay, and that's going to be kind of one of the things that we look at with these problems, as that argument changes, the parts in the parentheses, that should hopefully elicit the fact that we've got some identities that we've got to mess around with. Usually, with the argument changing, a lot of times people are going to want to have like a chart next to them of their identities and their formulas that they can use. They tend to be the ones that are used the most seldom, I guess. So we don't learn them as well as the other ones. But if I've ever sine negative x and I see that my problem, I don't have a chart to look at or a table of identities to look at, we can do this. Okay, well, if I have sine of negative x, well, negative x means I'm going in that direction, and sine is the y value, right? And the y value here, so this the x value would be positive, the y value is going to be negative, right? And we know on the unit circle, that should be the same thing as going x that direction. That y value is positive, right? So how do I make this y value negative? I multiply the entire sine function by negative, and that's where that comes into play. Does that kind of make sense? We've dealt with that with the symmetries of the unit circle before. I'm not going to spend a whole lot more time on that today, but that's how you could regenerate those even-odd identities if you forgot this. Okay? And then our cofunction identities down there at the bottom. Usually in a problem, we won't want to go from cosine x to sine of pi over 2 minus x. Usually they'll present us in our problem in the text, or on letter sign, they'll say sine of pi over 2 minus x. Somewhere in the expression, it would be very beneficial for us to recognize, well, that's the same thing as cosine x, and replace that thing with cosine x. Does that kind of make sense? Our goal is to make things look simpler. Start with something complicated, make it look simpler through substitution. And those relationships, those just come from the fact that the sine function and cosine function, they're just transformations of one another. Move them left and right, or reflect them, and you end up with the same curve. Okay? Cosine is a translation or a transformation of sine, and vice versa. Tangent is a transformation of cotangent, and vice versa. Secant and cosecant are transformations of sine. Does that make sense? Okay? Losing my voice for some reason. All right, so here's kind of the breakdown of what we're going to do. Try to maybe 2 or 3 sentences here, give you an idea of the process here. It says trigonometric identities allow us to rewrite the same expression in different ways. Okay, and you guys have done this with algebraic expression. You did. If I give you 2 times the quantity x minus 3, you will know that it's more beneficial to rewrite that a lot of times as 2x minus 6, right? Use your algebraic properties to transform. We do the same thing here, but with trigonometric relationships. Okay? So usually, this is in an effort to make something appear simpler in algebraic form. It says in simplifying algebraic expressions, we use factoring, common denominators, product formulas, and the same thing's going to happen with trigonometric expressions. Okay, but we're going to incorporate a lot of our trigonometric identities as substitution tools to kind of tie in all of these ideas together. Okay, a purpose of this, I think maybe a lot of this stuff, and this is just mathematics in general, a lot of this stuff kind of maybe developed initially because it's human curiosity. People have been worried about, and just kind of make a comparison here, people have been worried about prime numbers and thinking about them for thousands of years, okay? But it wasn't recently until like the advent of computers and encryption and stuff like that that we really found a practical purpose for very, very large prime numbers. Does that make sense? So when this stuff was first starting to develop and people were messing around with it, was there a huge application? I don't know. I wish I knew more background stuff about this, but something to think about is if I'm writing because a lot of programming, especially if you think about like coordinate programming with like GPS and stuff like that, uses a lot of sine, cosine, tangent stuff, a lot of location, a lot of indirect measurements. If I'm a computer programmer and I'm coding this program to do some type of calculation with angle measurements to develop somebody's location, and I've worked out the code and the algebra that it says cosine t plus tangent t sine t needs to be coded into this program. How many times do I have to input my t value there? How many times do you see t up there? 3 times. And it needs to be evaluated the cosine, it needs to then be evaluated the tangent, and then evaluated the sine, right? And then we get 3 numbers back, 3 ratios back, and then we multiply 2 of those together. Then we're going to take that product and add it to another one, right? So there's a lot of operations and a lot of inputs there that we need, okay? And if you think about somebody that's coding something, and you think about computers, that's a lot of RAM. It's a lot of RAM in your memory, right? It's a lot of computer power or power that's needed. It's a longer program, and for companies, that all boils down to more money. Does that make sense? Where if I'm a computer program and I want to be efficient, maybe I can do a little bit of algebra to simplify that. Make it maybe one input value. Okay, so let's try to see if we can do this. So simplify the expression cosine t plus tangent t sine t. The number one thing I think you guys should look at is powers. Okay, your exponents. Because if I get exponents that are greater than 1, most likely going to have to deal with these things here. Okay. Right now with this example, we don't have any powers greater than 1. So the next thing you want to do is rewrite every single trig ratio up there so that is in terms of sine and cosine. And what I mean by that, if I go back up to my blue chart up here, would you agree that cosecant can be written in terms of sine? Secant can be written in terms of cosine, right? Cotangent in terms of tangent, but tangent can be written in terms of sine and cosine. So then if that's the reciprocal, then cotangent can be written in terms of cosine and sine, right? And sine and cosine are already in terms of themselves. So every time we come across one of these things, if I've got powers of 1, I'm going to try to rewrite things in terms of sine and cosine. So that means that thing right there needs to be rewritten. Does that make sense? And once we rewrite it then, so I'm going to rewrite this as cosine of t plus, now tangent, now here's where we use an identity. Tangent is sine divided by cosine, right? So that's one of our purposes of identities, is to take something out, take tangent out, and replace it with what it's equal to. Use that substitution technique. Okay. Now, once you've done that, once you've changed everything in terms of sine and cosine, you want to go through there and you want to use your order of operations. Please excuse my dear Aunt Sally, right? And she tells us that you have to do what first? Say again? Okay, for this problem, since parentheses are up there, what are we going to do here first? We're going to do the multiplication first. Okay? So that's going to give me, when I do this multiplication, it's multiplying to what? That is a fraction, and this is a fraction as well, right? So you multiply two fractions. How do you do that? Straight across top. Sine times sine is sine squared. Straight across the bottom is cosine times 1 is just cosine, right? All right, now we've done the multiplication. Okay. The next thing, you see division up there, right? Okay. But the idea is kind of analogous to this. If I had, and I always go back to, if I struggle with what I'm supposed to do next, I always go back to like numbers. If I had 2 plus 1/3, would I actually do the division of the 1 and the 3? Or would I try to add those together? You try to add those together, right? So I'm going to try to add the two fractions, cosine and sine squared over cosine t, together. And if I'm going to add two fractions, what do you need to add two fractions? Common denominator. So what's that common denominator going to be? Cosine. Okay. Now, remember how we find the common denominators. We go through all the denominators and we take out every single new denominator that has the highest power, right? So each denominator needs to be represented. And here, cosine and 1 are those two. So I'm going to rewrite each denominator here as cosine t. So this one here, this fraction already has that denominator of cosine t. So I'm just going to rewrite that here. I'm going to transform this denominator so it becomes cosine t. So if I do that, if I multiply that 1 by cosine t, what do I have to do to the top? Multiply by cosine t, right? And why do I know I can do that? What did I just effectively multiply by? I just multiplied by 1. So I know I'm allowed to do this. So now I get this. That make sense? Okay. Now, when I do that, Purpose of coming up with that common denominator is so I can write cosine t as one denominator and then do the algebra with the numerators, right? So the algebra says cosine squared t plus sine squared t. Well, what is that? Yeah, we have an identity that says cosine squared plus sine squared. That's the Pythagorean identity. We know that that's the same thing as 1. So we make that substitution. And now what is 1 over cosine? And we're down. We usually know we're done when we get down to one trigonometric ratio left over. Okay? Would you agree that that is a lot simpler than what we started with? Yeah. Okay. And now from a computer program, you see, or programmer, you see that there I only need t to be inputted in one value, right? Or one expression. When I started, it needed to be put in a 3, and then I started doing operations, calculations with that. If I rewrite that code, that line of code as secant t, one, there's no operations that have to be done with it. It just has to evaluate what secant t is. One input factor. Okay. So it does a lot for us technology-wise. Now let's talk about how we can go and verify that we've done this correctly. Two things you can do. I would suggest not using GeoGebra for the fact that, yeah, right, at least right now, because GeoGebra, when I type something in, I got to type it in like this. It's kind of like typing in on a TIA 3 or 4. If I want cosine squared over cosine x, I got to type it in like that. And it doesn't tell me that I've typed it in like I want it to be typed in until I hit enter. Does that make sense? Where if we draw comparisons to Desmos, if I type in cosine squared, it's kind of got that math print. So as I'm typing it in, it's putting it how I wrote it by hand. Does that make sense? And that's the nice thing about Desmos, the one nice thing about it. All right, so what I've done here is I've just typed in this one here, right? This line of work. But what you guys can do with this is if you want to check, and hopefully you do, whether you've done this correctly, is you type in what you started with. So I started with, what was it, cosine x plus tangent x times sine x, right? And it gives me that. Now I'm going to type in what I finished with. And what happened when I typed the blue one in, the green one in? They overlaid on each other, right? And it tells you they are the same. Now here's the thing. If I would have typed it, that green one would have been different. I would not erase everything. Okay, and this is why when you do your homework, you want to structure things and you want to be in an orderly fashion when you go through line to line and do simplification. Because if that was wrong, if they didn't match up, I would go back one line and type that line in and see if they match up. Does that make sense? And if they don't match up, then I'll go back one more line. And then hopefully in that one they match up. So now I know where my error occurred. Does that make sense? And that's kind of how maybe computer programmers kind of go through things and try to decipher. You know, maybe they type code and they want it to do something, but it doesn't do exactly the way they want it to do. They start at the end and they go back, okay, and start to retrace their steps instead of just scrapping the whole thing, starting over. Okay, we'll spend a lot of time that stuff that is going over more examples with this stuff. And I think,